Once the signaling molecule has bound to its receptor, regardless of whether it's a membrane receptor or an intracellular receptor, now we can get to stage 2, or signal transduction, of this process of cell signaling. Stage 2, again called signal transduction, is essentially a cascade of molecular interactions that will relay the signal from the receptor through the inside of the cell to the target molecules that are supposed to enact some sort of function in response to having received the signaling molecule. So let's take a look at what exactly a signal transduction pathway is. Essentially, it's a series of proteins, typically, that are kind of like falling dominoes. And one protein will activate the next protein, will activate the next protein, until you get to the point where you can activate the final cellular response as part of stage 3 of cell signaling. Now, transduction oftentimes occurs in a series of steps. You would think that maybe this is wasteful or time-consuming for the cell to go through the series of steps, but actually multi-step pathways are advantageous to cells. Number one, they're advantageous because it allows for signal amplification. So think about it this way. If you have one signaling molecule bind to one receptor on the cell, and then that one receptor binds to one relay molecule number 1, but this relay molecule number 1 maybe can interact with 10 relay molecules number 2. And then each one of those 10 relay molecules 2 can interact with another 10 relay molecule number 3. So at this point, we have activated 100 of these relay molecule number 3s, which then go off and activate the actual cellular response, making it a very robust internal signal inside the cell, while we only had one signaling molecule bind to the outside of the cell. So it can allow for signal amplification. And then number 2, another reason why multi-step pathways are important, it provides opportunities for the cell for coordination and regulation of cellular responses. If you have to go through a series of steps, there's a lot of places where the cell can say, oops, just kidding, never mind, I didn't really want to activate that, and it can stop the pathway before you even create the cellular response. Or sometimes signaling pathways can also branch, and so that'll allow the cell to figure out where it wants that signaling pathway to branch and what ultimately needs to be started or maybe stopped within the cell. All right, so just one more look at these signal transduction pathways. Again, you're going to have the signaling molecule that has already bound to the receptor. The receptor changed shape as part of step 1, reception. And then, like falling dominoes, the receptor activates the first molecule, which activates the next molecule, which activates the next molecule. And in this example, there are 3 relay molecules, but ultimately, depending on the pathway you look at, there could be more or less of those relay molecules involved in getting to the final endpoint, which is that cellular response. Every time a relay molecule gets activated, most frequently that activation is in the form of a shape change for that relay molecule. So the interaction with the previous relay molecule will allow the subsequent relay molecule to change its shape, get that active state, and then it can go on and do its job by interacting with the next protein or relay molecule in line. Now, how does one of these relay molecules get activated? Well, sometimes we can employ what are called phosphate groups, right? This should ring a bell. We've talked about phosphate groups before. We've talked about how they can function like molecular on-off switches, right? And so here's a great example where some of those relay molecules can have a phosphate group added to them or taken off to activate or deactivate the molecule. So let's talk a little bit about this process of adding a phosphate group or taking it off. If you're going to add a phosphate group, this is called phosphorylation. And if you're going to take a phosphate group off, this is called dephosphorylation. Now, to speed up the process, as with any other chemical reaction, the cell can employ an enzyme. There are enzymes that will perform phosphorylation reactions, and there are enzymes that will perform dephosphorylation reactions. Now, here's where a little bit of mental gymnastics comes in. Phosphorylation is going to be performed by proteins that are called protein kinases. Protein kinases specifically have the ability to take a phosphate group off of an ATP and add it to another molecule. This is called phosphorylation. And so many relay molecules actually in a signal transduction pathway are protein kinases. And what this does is it creates what's called a phosphorylation cascade. And we'll take a look at this here in a second. But essentially, one protein kinase will phosphorylate the next protein kinase, which activates it. And then it phosphorylates the next protein kinase in line, and so on and so forth. Now, where the mental gymnastics comes in is that there are enzymes that are called protein phosphatases. You would think that the phosphatases would phosphorylate, but no. The protein phosphatases dephosphorylate. So a protein phosphatase will take a phosphate group off of a protein. Typically, this will inactivate it, not always, but typically that'll inactivate the protein once the phosphate group has been removed. And again, this is called dephosphorylation, the removal of that phosphate group. Let's take a look at an example of one of these phosphorylation cascades. So here we're looking at the cell membrane. We've got a membrane-associated receptor here. The signaling molecule bound to the receptor and activated the receptor. From here, the shape change of the receptor can activate the first relay molecule. You can see it glowing here. This first relay molecule will then activate the first protein kinase in line. Once this protein kinase itself is activated, remember a kinase adds a phosphate group to other proteins, and it'll phosphorylate this inactive protein kinase using a phosphate group from the ATP. It makes protein kinase 2 active in the phosphorylated form, which can then activate the next protein kinase in line, again by phosphorylating it, and protein kinase 3 can then do the final activation of the last protein that will elicit the cellular response. So this is that phosphorylation cascade where you have multiple kinases in a line, and each one will then phosphorylate the next one, activating it, phosphorylating the next one, activating it, and so on and so forth. Now, many of the examples that we've looked at thus far at these signal transduction pathways involve very large proteins. It's hard for a protein to get through the inside of the cell using just diffusion. Proteins are big and it takes them a while. They encounter a lot of friction on the inside of the cell. So in some cases, some of these signal transduction pathways don't actually use a lot of proteins, but instead might involve small molecules that are called second messengers. So second messengers, by definition, are very small, non-protein and water-soluble molecules like ions that can be released in great quantities and can spread throughout the cell via diffusion a lot faster than proteins can. I'm not going to spend a ton of time talking about second messengers. Know that they exist. Know what they are. There is a section in your textbooks if you wanted to read up a little bit more about them. But second messengers, two examples that you should be familiar with are, number one, cyclic AMP. AMP is another sibling of ATP. So ATP is adenosine triphosphate. Take one phosphate off, you have ADP, adenosine diphosphate. Take off another phosphate group, and you're left with AMP, or adenosine monophosphate, with only that one phosphate group left. So cyclic AMP, this is a very small molecule, and it can be used as a second messenger, or cells like muscle cells. They use calcium ions also as second messengers. So again, they can be released in great quantities. They're really small. They're water soluble, so they diffuse really fast through the inside of the cell, getting that cellular response initiated really quickly.